A great pleasure to introduce Gunnar Carlsson, who will be giving our first talk this semester. So as you know, Gunnar is certainly one of the leaders in applied topology, and we're grateful for his work in simulating activity in this area. And he's both at Stanford and now also at IASD, which he helped found. So thank you very much, Gunnar.
Okay. Thank you very much. And it's nice to do this again. I guess I did this about a year ago when it was much more primitive, and we did it on the whiteboard, and I think this is better. So anyway, let me go ahead and start. I want to talk about local to global principles in persistent homology, which is the title. And I want to give you an idea of what we mean by that. How do I mean by that? So observation is that computational topology is currently very computational. And of course, that's kind of an obvious statement, I suppose, but what I mean by that is that it is that we are typically compute directly from the definitions. So we're performing calculations, chain complexes by doing the straight linear algebra on the chain complexes, including all the simplices and so on. And making those very efficient. So, by the way, I'm not trying to say there's anything wrong with that. I think it's excellent. What I'm talking about in this talk is to sort of add some additional abilities to the toolkit. So it turns out that ordinary topology, and so what I couldn't find the right adjective for it, mainstream topology, the things that people have been doing for years or 40 years, before the advent of sort of computational and applied topology. One did not have the option of computing directly. In fact, I mean, the definitions for regular homology are such that you're dealing with infinite dimensional vector spaces, dimensional, infinite rank abelian groups. But even if you do triangulations, typically the calculations trying to do them by hand is kind of hopeless. It's much too slow. And so what was done instead is to say, let's try to compute somehow indirectly. Let's try to compute make some small calculations and then leverage those in certain ways to get bigger calculations by assembling the smaller calculations together. So the main one, or one of the big ones that comes to mind, is the Meyer-Vietoris sequence that you're doubtless all familiar with. When you have a space that's built up as a union of two spaces y and z. Again, some mild hypotheses. Let's not get bogged down. But what it does is it produces then a long exact sequence of the type that I'm showing there. So what that does is it computes the homology of X in terms of three kinds of things. It says that it's the homology of the two pieces, homology of the overlap, and also the induced homomorphism from the inclusions from y intersects z to y z. So once you have that information, it doesn't necessarily give you precisely hi of x and a. If it's not field coefficients, it might be that there are some extension problems that arise in here. So, where it's hard to disambiguate between a Z2 cross Z2 versus a Z4. But nevertheless, it gives, very field coefficients, for example, it gives complete information as to the abstract structure of HI of X and A, given that other information. So this is what we call the local to global principle, because what it says is we try to understand global information about X from local information, namely the pieces and the overlaps. An analog when we have a covering by more than two sets, and in that case the output is not a long exact sequence, but instead a more complicated object called a spectral sequence. In other words, if I have a covering by 10 sets, I get this spectral sequence, and what it does is it uses all the sets in the covering, all their sections, all the induced homomorphisms among inclusions of these sets, an initial approximation called the E2 term. What one then does is to obtain the final answer requires the computation of some additional linear maps, so-called higher ordered differentials. And when you do that, at the end of the day, you end up with something that you would call the E-infinity term, which is a good approximation to the homology of the total space. Only that, again, there can be these extension problems. But you have field coefficients, for example, those problems exist. And you can get the total structure that way from the infinity. So here, since now can cover by more sets, those sets can all be relatively small and reasonable. You might say, looking big, we have to compute all the sets, cover all their intersections. Well, yes, but typically in many situations, the intersections turn out to be empty. And furthermore, even though this is relatively large, it's nowhere near the size of the explicit calculation using doing the simplices directly. So they'll call the local to global principle. A way to decompose a space is as a product of two or more spaces. So if I take X and Y, I can take a product. The question is, can we describe the homology of a product in terms of the homology of the factors? And I think probably all know that when we have field coefficients, describe the homology of the product. The Kenneth formula, which says, as it's written there, Hn of X cross Y is a sum of pieces of the Hi of X with the n minus I of Y. So it's this kind of sum. Kenneth formula for field coefficients, and it's also an extremely useful thing. This is different. This is a description of a product in terms of, instead of a coproduct, which is what one could have a union as. Now, there's a wrinkle when you deal with the Kenneth formula, not for field coefficients any longer, but integer coefficients. Then there's also a so-called Tor term. Tor is the first derived product of derived functor of tensor product over the integers. And it turns out that you can actually then get the exact sequence here. It's actually split. So, there's an explicit description, again, Hn of X cross Y with integer coefficients in terms of these two chunks. These methods, both Myrivotorus and Kenneth, are examples of indirect computational methods. In the Myrivotorus, what it says is, I'm going to compute some judiciously chosen, compute them all, and work with those chunks to assemble the global calculation. And really, the Kenneth formula says, well, look, if you compute the homology of X and Y individually, you can extract the homology of X cross Y actually from that. So the being again that there's a lot of value in computing large chunks of information and trying to assemble. We claim that for those parts, these ideas have not yet been exploited in applied topology, and I think that there is value both from the point of view of making quicker computations, but also of gaining overall understanding. When you understand these larger scale relationships, it becomes it gives understanding that sometimes is missing when you're doing kind of direct calculations.
Question. Do you see a natural place for products of spaces showing up in the use of applied topology that we're doing right now?
I'm going to talk about it. I'm going to talk about that actually. It'll be part of it. Yeah, we're going to look at both. We're going to have examples of excision and Myrivotorus, but we'll discuss what should the Kenneth formula be in persistent homology, for example. Okay. Okay, good. So here's the first question then. Here's the first, indirect question. Can one compute the persistent homology of the metric space X, that is the union of two subspaces, Y, Z, from the persistent homology of Y, Z, and intersect Z? So what I mean here is X is equipped with a metric. The restriction of the metric to Y and Z makes them into metric spaces, also to Y intersect Z. Is there a way of computing the persistent homology of X using that information and perhaps some inclusion there? The answer is clearly no in general. If you look and think about it, there's no way that could work. because there are different metrics on X which have identical restrictions on Y and Z. So the problem is ill-posed, right? In other words, just if you know the restrictions to Y and Z and Y intersects Z, there are many different metrics on X which have those same restrictions. And so we can't hope to recover the persistent homology of X from that of Z and Y intersects Z at this level of generality. For one thing, there is a maximal metric on X which restricts to the given metrics on Y and Z. This is something Gromov has constructed. It's not hard to see what it is. Once you ask yourself what such a thing is, the definition is just written as as an infimum over certain sequences. So think of that as a push-out metric, so that on Y union Z, which is X, there's the push-out metric of Y and Z over Y intersect Z, where these things have the restricted metrics. And so now this is a well-defined metric on the two metrics on Y and Z, and which restrict to Y intersect Z on the same metric. And so now it is at least conceivable that one could compute the persistent homology of this metric on X from the information about Y, Z, and Y intersect Z. And so one might hope that the persistent homology is computable like this. I don't know the full answer to this. I'll be talking about some analogous things, but I think this itself is actually quite an interesting question that one could attempt to address. And I'm going to show some methods that get at this that are useful. So the question is, what should we expect? Well, maybe what we should expect is a long exact sequence of persistence vector spaces over a coefficient field K here. Let's assume that when we do persistent homology, we'll always be doing it with respect to a field of coefficients. And so this is what we might expect here, the persistent homology migrator. It's an exact analog. So this would be useful for a number of calculations. So for example, if I have a tree, I choose vertices as the points of my metric space, and I'll compute the distance between 2 points as being the length of the shortest path in terms of the number of edges involved. And the wedges could even have weights here. So this would be very useful in that situation. And we see that it works in this situation. As I say, we don't know if this is true in general, but we'll have similar results in some cases. Okay, now let me just talk about the technicalities here, which I suspect everyone on the call knows. Simplicial complexes are defined in the usual way. Now, we can talk about a notion of a collapse. So given implicitly sigma with tau, with sigma a face and equation one face, and tau a maximal simplex, we can remove both sigma and tau to obtain a simplicial complex whose inclusion into the original complex is a homotopy equivalence, provided that sigma, and I haven't mentioned this here, provided that sigma has the property that it's only contained in the maximal simplex it's contained in is tau. So that actually should be in here. I didn't include it. So I think we're all familiar with this kind of thing. The complex obtained by removing sigma and tau is called the endpoint of the collapse. And so here's the situation. You can see sigma, it's the only maximal simplex that's contained in is tau. We're allowed to remove sigma and tau, and in fact, the statement then is we don't alter the homotopy type of the underlying space, and therefore we don't alter the homology. So now suppose we have a finite metric space, and recall the Vittoris-Rips complex of X with threshold R is defined as familiar here. For threshold R, R of X and R, of course we have these inclusions as usual, VR of X and R and VR of X and R prime whenever R is less than or equal to R prime. And so we can think then of VR of X blank, the functor with the values of R is a persistence object in the category of simplicial complexes. So a persistent object is just a family of objects in whatever category you have, comprised by the negative integers, and with mass supplied whenever from the rth object to the r prime object whenever r is less than or equal to r prime. So we'll suppress the r and think of it as an object here that now what we'll talk about is the notion of a filtered collapse. So filtered collapse of a filtered simplicial complex is a collapse of the overall simplicial complex, which is the whole thing. It's contained in tau, but has the property that the filtration of sigma is equal to the filtration of tau. So in other words, if I have a triangle and the edge appears simultaneously with the triangle, and all that edge is contained in only that triangle, then that is a filtered collapse. Again, there's R equals 5. Let's see. Yeah. So equals 3. Yeah. So what I'm talking about here is that there's going to be a statement that says that have a filtered collapse. The complex that is the endpoint of that filtered collapse is also a filtered subcomplex, and the persistent homology is isomorphic to the persistent homology of the whole thing. So the way you prove that is you prove that at every level that happens. So in this case, say R equals 5, the collapse might look like this, but now R equals 3, it could look like this because that big simplex, that big triangle, and the vertical edge have not been introduced yet. So in this case, it is kind of a trivial collapse at R equals 3, whereas at R equals 5, there's actually a collapse to be done. But in your case, what happens is that the inclusion is an isomorphism on the the complex, the filtered subpiece for R equals 5 or R equals 3. In the first case, because it is actually a collapse, and in the second case, because, well, they're the same, they're identical complexes. So that's kind of a sketch of filtered setting. So there's a filtered simplicial complex, and the inclusion of x prime into x induces an isomorphism on persistent homology, and you have a filtered collapse. Okay. And so I'm going to just sort of sketch the proof. This is, as I just did. It is clear that the collapse either restricts to a collapse on x of r, or neither simplex in the collapse is contained in x of r, so then x of r is contained in x prime. The second, r equals x of r, so we're done. Okay. So this technical result that I just described, this is a result for filtered simplicial complexes in general. This technical result turns out to be applicable to the case of some Vietoris-Rips complexes. Certain situations we'll be able to show that Vietoris-Rips for a finite metric space is equivalent to a pushout of Vietoris-Rips complexes of subspaces. And actually, I say certain situations, but actually it's pretty a lot that you can do. So, here is as in the category of filtered simplicial complexes. Let's look at this. Then it's a very simple thing to prove, but it turns out that you can do a lot with it. So let's suppose that X is a finite metric space, and let that X0 and X1 denote distinct points in X. And let VR of so Vietoris-Rips of X, but relative to the 2 points X0 and X1, threshold R denote the subcomplex which consists of all simplices which don't contain both x0 and x1, but they might contain the one or the other. And let me do the following. Let x0, x1 denote the result of removing x1 and x0 points separately. So in other words, I've got a space x, and now I've got a space x0 with one fewer point in it, and I've got a space x1 with one fewer point in it. And the complex VR of x and x1, comma r is the union of the two subcomplexes VR of x0 r and VR of x1 r, with intersection the x0 intersect x1 and r. That's easy, you can see, right? If you're not allowed to include both x0 and x1, then I could include x0 or I could include x1. Either one of those will be contained inside their VR of x0 and r and VR of x1 and r. And the section is clearly as I described it there too. So choosing the 2 points allows me to specify a decomposition of x into 2 pieces. Notice the 2 pieces are quite big. They each are moving only a single point, but it is a union like that. Okay. So here's the theorem. The theorem says that suppose that x and x0 and x1 are, as in the previous slide, also that the cardinality of x is greater than or equal to 3. You'll see why that is necessary here in a minute. And that therefore x0 intersect x1 is non-empty. Okay. Suppose that suppose that x0 and x1 in fact realize the maximal distance that first in the next equal to the maximum value achieved by d. So that's r. This inclusion of VR of x, x0, and x1 into VR of x is about the equivalence of filtered simplicial complexes, and in particular induces an isomorphism on persistent homology. Now, so this is a good thing, because what tells you now is that it says that you've got VR of x on the one hand, but now VR of x, x0, and x1 is a filtered simplicial complex in its own right, and it has the same persistent homology as VR of x, but its property, the left one again, VR of x0, x0, and x1, that it breaks up as a union of filtered complexes and therefore will provide a torus sequence. We'll see. So x0 and x1 as in the previous slide. There is this long Meyer-Torus sequence of persistent K vector spaces that look like this. Okay, so that's a useful thing, as we see. So what's the proof? How do I show that this inclusion of VR of x, x0, and x1 into VR of x is in equivalence? Well, what we do is we need to understand all the simplices in VR of x that are not in VR of x, x0, x1 in order to construct a collapse sequence, so a filtered collapse. It turns out that this is not a difficult problem. These simplices are in one correspondence with subsets S of x minus x0 and x1, including the M set. Due to the cardinality condition, x minus x0 and x1 is non-empty. And the correspondence is just, well, any subset of x minus x0 and x1 gets sent to S union x0 and x1. So the empty set, for example, goes to the set x0 and x1. So this is an objection. What you can now do is you can impose a total order on x minus x0 and x1, Z. I'm just going to order those points. Using a lexicographic ordering, I'm going to form a corresponding total ordering of the collision of all subsets of Z, the property that it's consistent with the partial ordering determined by the cardinality. So we're going to say larger cardinality sets occur before smaller cardinality sets. What this allows me to do, it allows me to provide a list of simplices. So the first one is the maximal simplex. The second one is a codition one face, the maximal in the order, and that turns out to be a filtered collapse. and then I take the next element in the order is the next largest set, and I find a filtered collapse inside that. So in any case, let's look at it. Now we have an ordering on all the simplices, VR of X, and not in VR of X, X naught, X1. The great observation here is that because each simplices contain both X naught and X1, their filtration is R. It's that top maximal distance in the metric space, because X naught and X1 is contained in it. So what that means is that if I can do a collapse sequence, because they all have the same filtration, it will, of course, be a filtered collapse sequence. The maximal simplex, all of X, select the maximal codimension 1 face in the ordering defined earlier. Gives collapse. Simplices have filtration R, so there's only one maximal simplex. That maximal simplex and the chosen codimension 1 list from the list of simplices. Select the remaining simplex in the ordering and maximal codimension 1 face. Easy to check that this is also a collapse sequence and therefore a filtered collapse because they all have the same. You chosen simplices from the list. Now you kind of repeat this over and over until all the simplices are gone. So you can check that we filtered collapse at each stage. And when the cardinality of X minus X naught and X1 is 3, you would start out here with this maximal one, and then do this, this. This would be the collapse sequence in the case. So in this case, I'm labeling the elements in X minus X naught and X1 by subscripts that are involved. Okay. Yeah.
So this looks almost worryingly powerful. The reason why I shouldn't expect to be able to repeat the entire thing over and over again until I reduce all generic data sets down to 3 points?
Yeah. So here's the statement. So that is what happens. Here's what you need to. When you first observe that cardinality of X is 2, okay, this does not work. Okay, if you look at it, you see that there is a failure of this to happen in that case. And so now, when you start iterating this process, so the first time you break up the metric space into 2 pieces. When you do the process, do it again. Now you get a diagram, a 2-dimensional diagram, a square diagram with 9 nodes, 1 in the middle and then along the edges. And similarly, when I do it the third time, I get a cubical diagram. And what starts happening is, as you get down further and further, at certain points you start to have cardinality 2 subspaces appearing. At that point, the thing fails. What you can actually do, though, is you can actually track the failure and build that into the diagram. So it is quite powerful, but what it does is it presents new complexes for getting at it based on these kind of cubical diagrams. Does that make sense?
Yeah. Thank you.
So good.
Yeah.
So in this, if we change this example by just looking at the boundary of the 2 simplex, right away, right? So we can't make any simplicial collapses. Where does that contradict your assumptions? Or
well, boundary. Let me say. So that's not Rips complex of anything.
It's not the Rips complex. Yeah.
Yeah. By the way, let me just say, just to step back for a second. So we're used to thinking of we do the topological computation when the input is a topological space. Now, for the input is a metric space, so we expect that there's going to be a lot more complexity around the Meyer-Gatoris here for various reasons. Just like one does there's a setting which some of you may be familiar with, where one studies varieties over, say, over finite fields, for example, and try to do cohomology of those. Okay, and then you find also that Maya-Vitoris has no restrictions to it, and so on. So, in general, when one uses homological methods to address problems in combinatorics or whatever, one expects that the reduction principles will be different, more complicated, more restrictive, and whatever. Yeah. Okay. Now, I did some joint work with Raul Rabadán and Joe Chan on evolution. Where the data sets, hypotheses around the data sets is that they should be they'd be tree-like. So genetic study sets of sequences of classes of organisms, uses Hamming or weighted versions of Hamming distances, an organized principle. And there's been a feeling going back a long way, even before Darwin, I think, where one sort of believes that somehow life should be a tree. I think even if you go back to Linnaeus, for example, you'll sort of find hints in that direction. But certainly Darwin talked about the tree of life. And so what one expects here is, in certain situations, is that that one should be approximating the space by a tree. Is this always justified? Now, the way that people who do phylogenetics work is to find the best approximating tree and say, well, look, this is what we believe is the right approximation. It's a little like doing linear regression, but it's like tree regression instead. And the question is, though, there are metric spaces, obviously, that are not tree metric spaces. Is it possible that the metric spaces that come up in when you study real life sequences, maybe there's always trees, and in fact, it's going to turn out that they're not. But so what you want to do, you might want to say, instead of trying to fit a tree, you might want to ask, is there a way of measuring somehow the degree to which something is close to being a tree? Something an a priori calculation that doesn't go along the lines of trying to fit or optimize anything, but is a flat-out measurement sitting there. Okay? So this term here is a contribution to that statement. I should say, so T is a tree, and perhaps it's a weighted tree with lengths assigned to the edges. So then any finite subspace of T, in fact. So I can actually take points on the edges. Persistent homology vanishes for every I greater than 0. It does not say that the bars are short. For I greater, it says there are no bars. If I have precisely a tree, there are no bars in dimensions greater than 0. Very effective thing that if you have a metric space and you measure it and you see that there are bars in higher dimensions, and one realizes that there might be noise and so on. So if you find that there are no long bars in higher degrees, that there are long bars in higher degrees, then you know that it's not a tree. This is an illustration from that paper. It turned out that I won't go into the details about the evolution. There are various mechanisms for evolution, of which the one called clonal evolution is the one that produces tree-like things, and then the other things that produce features in these sets. And those we observed, and it was quite an interesting paper. So the standard model is complete. A signal for the principle of alternate mechanisms, such as horizontal gene transfer. What's really interesting is that you can get certain evolutionary rates out of the barcodes, and also, in fact, the generating cycles for the homology classes contain clues about where the horizontal or the exotic evolution occurred. So that was pretty exciting. We don't have any way of justifying that at the moment. In particular, the algorithms for computing persistent homology, of course, we understand well the way the cycles that get created there. So this is just an observation, a useful one, or an intriguing one. It says that maybe you can try to get into the bottom of, well, do these algorithms produce somehow minimal loops in this context? And, so one expect the minimal loops to contain the places where the exotic evolution occurred. Okay. But what I want to talk about, how to prove a weaker form of that theorem. That theorem is great as it is, but it says that allow points to lie on the edges. We're going to take a weighted tree and we're going to take the vertices of T, and we're going to talk about that kind of metric space. So the T as a filtered simplicial complex, each edge is assigned a filtration given by its weight. Okay. In other words, I'm not including any simplices if X and Y are not connected by an edge but are connected by a path. I will never connect them by an edge in this setting. So T itself is sort of patently zero-dimensional, right? It will have no loops in it. So it is a filtered simplicial complex. It is not a Vietoris-Rips, but it is a filtered simplicial complex, and it has, vanishing present homology in dimensions 1 and bigger. But it can have H0, which happens, at the very low levels, all the points create a lot of H0, and then, as the tree, you increase the filtration, you will start collapsing points together. But you will never create loops because it is a tree. Furthermore, there's a natural map of filtered simplicial complexes like this, so JT from T into VRT. And it's clear, right, because you have things that are connected by actual edge of certain filtration, and they will also be connected in the Vietoris-Rips. Vietoris-Rips is much bigger, though, because at some very high level of filtration, for example, it will include, huge simplex. So this is an inclusion of a small complex into a big complex. But the idea is to try to prove that this map induces an isomorphism on persistent homology. Notice if we prove that, we're done because of the observations I just made about T cell. This map induces an isomorphism on persistent homology. So the plan is what we wanted, that the persistent homology of tree metric spaces vanishes in dimensions greater than 0. Okay, suffocation, if you like, for that. Well, here's the thing. The proof of the theorem is there's a notion of push-out for filtered simplicial complexes. So it maps of push-out diagrams. So if I have two maps of, if I have a map of push-out diagrams of filtered simplicial complexes, then I will get a corresponding map of the pushouts. So given a tree, let's find a pair of points that maximizes the distance function on the tree. So we're going to find this T0 and T1 analogous to the X0 and X1 that we had before. And it's clear, if you think about it for a couple of seconds, it's going to be clear that from the piece of trees, that T0 and T1 are leaves. So they're contained in only one edge. So T0 and T1, and a picture of how it might look. Here's what we have. We have a map of push-out diagrams that looks like this. So I take the T0 and T1. I know it is clear that T is the push-out of T0 intersect T1. T0 and T1 over T0 intersect T1. In the same way, I can take the maps on the Vietoris-Rips complexes. I can get a map of push-out diagrams like this. Now, T1 and T1 intersect T1 all have cardinality less than the cardinality of T. So this kind of picture can be the basis for an induction, reduced ultimately to a two-point tree. So what I'm saying here is, let's suppose that we've proved the result that, that the map JT, this one, sorry, both proven that for all trees smaller cardinality than T, J of that tree is an equivalence on persistent homology. So now we've got a map of pushout diagrams like this, and each of those vertical arrows are maps which are by the inductive hypothesis that is using isomorphisms on persistent homology. Okay. So what that says is that the pushout of the top, which is T, to the pushout of these two in the pushout of the lower row is an equivalence on persistent homology. But the pushout of that row, that is just exactly that subspace that I talked about, the VR of T, rel T0, T1. And so it is known to map equivalently to the to the Victorious Rips of T itself. So that actually result then, because you can perform this induction until you get all the way down to a 2-point tree, and then the two are actually isomorphic. So it's a really simple proof because you kind of looked at it. It doesn't involve much messing around with anything. It simply allows you to, the thing that you want is recognized by a map from a simple object, namely T, to a complicated object, the Victorious Rips. Products. Mikael asked about that. So metric spaces can be defined in numerous ways, right? So for metric spaces X and Y, we have the metrics. We can take max of dx and dy. We can take dx plus dy, so forth and so on. So there are lots of different metrics on the product. Can one compute pH star on any of these products in terms of pH star of X and pH star of Y? Well, so we consider the case of dx plus dy, and we can see that there's a natural guess to make here, a natural thing. So, and the question is, what is it? What would one expect from a formula in this setting? And it's useful to go back to sort of mainstream topology and understand what happens when I deal with generalized cohomology theories. So cohomology theories that are not just ordinary homology, but that might be like K-theory, Buddhism, and you've heard of these terms, BP theory or Morava K-theory. It turns out that what they admit is not Kenneth formulas, but they are spectral sequences. And in the form, it looks like this. So the E2 spectral sequence looks like Tor over G star of point. So G star of point here is a ring. It's a weighted ring, but it's a ring that won't just have Tor 0 and Tor 1 the way the integers do, but have Tor in all possible higher dimensions and a sequence like this. So it's much more complicated, but it's quite interesting. So that is what happens when you have generalized cohomology theories. So the question is, so what should we expect for persistent homology? That the category of persistence modules is equivalent to the category of modules over a graded ring. So in this case, it's an R plus graded ring over K plus. So that is something that one can prove, and the modules arising from a finite metric space have a certain finiteness condition. They are finitely presented, so the complexes will always consist of finitely presented modules, and so will the homology. It's out that the finitely presented modules over this ring have barcode classifications, and because they have length 1 free resolutions. It's out that just like for the integers, if I'm with with finally presented modules over K of R plus, then Tor I has the same vanishing property, I greater than or equal to 2, that the ring that it does over the integers, but it does it for this ring instead. So this ring K of R plus is very much analogous to the ring of integers, or the ring T that we sometimes use when we deal with integer values. This yields a Kenneth formula for tensor products of plus graded complexes. So if I take chain complexes of R plus graded modules, here is the Kenneth formula, and it's just very much analogous to what happens with integers. There's a Tor term here, but it's the Tor term over K of R plus instead of the Tor term over the integers. So there's So this is the Kenneth formula for chain complexes. Sequence turns out to be split. Same argument as is done in the normal case works very nicely there. Okay, on the other hand, tensor products of R plus filtered vector spaces. We can write that down as well. Let's see. So filtered vector space equipped with filtration like this. Split in two filtered simplicial sets. Products in Y can be equipped with a filtration like this. Persistence is directly computable using the Kenneth formula. So if I take filtered simplicial sets, and take their product like this, in a sense, that's equivalent to the tensor product of the complexes of the two X and Y, of the two filtered complexes. Consistent homology precisely has the same Kenneth formula that I wrote down before. So this is where the input is filtered simplicial sets and therefore filtered chain complexes. Okay, so good. Consider a product of two metric spaces X and Y with a sum metric. We use a simplicial set model. Just it turns out that works better here because it works better for products. K-simplices in the simplicial set model ordered K-tuples of elements in the metric space. And filtration of X0, X1 through Xk is max over Ij of D of Xi. On the other hand, the underlying complex here of R of X cross Y, it is the product, and set the typo there. And the filtration is given by max of X of Xi and Xj plus dy of Y and Yj to be the filtration. So on the other hand, the filtration in the product of the two filtered simplicial sets is the sum of the two maxes. What happens is that they will sometimes be equal. One is in general less than two, and so the overall complex is precisely they're identical. The filtrations are somewhat different in the tensor product and the torus of the sum metric. There's a natural map of filtered simplicial sets like this, not an isomorphism in general, not in general a homotopy equivalence of filtered simplicial sets. So the thing on the left is now the thing whose homology we can compute by the Kenneth formula, and it maps to the homology of the product with the sum metric, but it is not an isomorphism of chain complexes. When does the Kenneth formula hold? I'm going to give you some very simple example. Product of two metric spaces of cardinality 2. So, a box, rectangle. Product of two lines works. So, if you have, two, is to say, a line meaning, basically the metric space attached to a tree which is only a single line. It looks very likely, I believe I can prove, that it also holds on a product of two trees in general. The product of the two metric spaces of two trees actually works the same way. It fails for where if I is a two-point metric space for, say, I squared cross I, where I is whereas it's two-point metric space. So that's interesting. It fails, and it fails kind of dramatically. So in general, it fails for n-fold products of I, where I is a two-point metric space. Okay. What happened? Okay, I seem to have. Let me hang on. Unfortunately, something's gone wrong technically for me here. Oh, there we go. Okay, good. Now, to compute the persistent homology of a tree. So, an optimistic conjecture about what might happen. We were able to compute the persistent homology of a tree. There's an isometric embedding of any tree in L1 to the n for some large n. So L1 to the n means like the taxicab metric space. So in n dimensions. Tree is a cubical complex with only cubes of dimensions 1, 0. embedded in a cubical complex then as a convex subset, is what that's telling you. Question then is, what we did with the tree, we found this space which was the underlying cubical complex of the tree. In that case, the cubes were only of length 1, they were only intervals. But that complex, its persistent homology was identical to what you got in the, for the persistent homology of the metric space. So here, if I say I take a product of two trees, well, that can be viewed as a cubical complex of dimension 2 or cubical complex of dimension 3 and so on. The thing that one can ask is, supposing that you have an understanding, that you have a complex which is embedded as a convex subset inside L1 to the n. Is it possible that the persistent homology of that cubical complex itself is isomorphic to the persistent homology of the corresponding metric space? And I don't know the answer to that, but there are strategies in mind. What does get required here is that one understands the persistent homology of the cube. So the one cube is easy. So positive dimension barcodes vanish, single bar, of length equal to the length of the diameter of the metric space. The 2 is also easy, and you find that it is indeed predicted by the Kenneth formula. That was what I mentioned before. But the cube, not to be what you would get from the Kenneth formula for a threefold product. So in general, it turns out what happens is that the n cube should have highest non-vanishing barcode in dimension 2 to the n minus 1 minus 1. That can be proved using the methods that I just talked about. So you can perform these reduction steps for that cube to get it down to a complex of this size. So notice that's much bigger. What would be predicted by the Kenneth formula in general, be classes in dimensions n-1. The top class would be in dimension n minus 1. And here it occurs in 2 to the n minus 1 minus 1. Here's, again, the cubical complexes admit a presentation like this. CIs are the maximal cubes, and I0 and I1 are the inclusions. Applying the Vitoris rips, we would obtain a similar diagram. And there's a method from this pushout to Vitoris rips of X and blank will be called cubical assembly. And so the question is this cubical assembly map is in fact an isomorphism on persistent homology. And here I'm stating what the earlier results on trees can be interpreted as saying that this is true for one-dimensional cubical complexes. So the conjecture is that one can extend the result to finite-dimensional cubical complexes that are convex subsets. We'd massively cut down on the calculation for such complexes and go on to reason about products of trees since they always have this property. So that is what I had. So I'm happy to answer any questions.
Thanks, Gunnar. So do we have questions from the end? Maybe so you do so free we could include it into the corresponding Vitoris complex on that tree. So that's functor from ways to Vitoris rips complexes, I guess. So inclusion functor, and it respects colimits.
Well,
functor?
Well, the map it affects it in the sense that that you get a map. If you've got a pushout diagram of the complexes, I get a pushout diagram of the corresponding Vitoris rips complexes. But the key step is to say that pushout of Vitoris rips complexes is equivalent to, but not isomorphic to, but is persistent homotopy equivalent to the the rips on the pushout. So Vitoris rips to Vitoris rips to the pushouts. That's the key piece, and that was the thing that I proved in that in that lemma. That is what makes it work.
questions?
Okay.
One part that maybe you could say again, I think I missed it. In one of the earlier theorems, you had this is a theorem on the morphism for the Viator-Scripps complexes. There was a condition on the 2 points x0 and x1,
Oh, yeah.
and that was that I think you said maximum, so that distance was the maximum value achieved by d.
Correct.
Can you explain, please?
Right. So here's the thing. See, so let me push back here to this. Let's see. Anyway, so yeah, here's talking about. So, just choose 2 points in the metric space. The unit result is not going to hold, and the reason is that if an x1 are not maximal, the distance between them is not maximal, then I can't start it because I can't have it be the case that I'm building filtered collapses at all. In other words, it's only when if x0 and x1 have distance r, where r is that maximal distance, then it's that any simplex containing x0 and x1 must have the same filtration, and so have the same filtration, and so that allows me to do this kind of collapsing, because I always know that it's the same filtration. If otherwise, I would have, if x0 and x1 were smaller than that, then there would be things that were bigger, that the filtration would vary. And so I couldn't build the collapse sequence. That sequence, that is, requires that, that the big flex and then its codimension one face have the same filtration. Sure.
The definition of a filtered element collapse was just an collapse, but you require it collapse onto stages earlier in the filtration or at the same level?
Identical level.
Identical level, okay. The second question was, I was confused on the cube because I'm trying to see why there are classes in degree 2 to the n minus 1 minus 1.
Yeah, on the cube, it is simply, you take the cube, do it as the set 0 and 1 to the n, and it's the the Hamming distance, if you like, between two sequences. So look, I was I didn't believe it at first. The truth is, I thought for quite a while that the Kenneth formula was just going to hold. Look at it. You start to examine it in dimension 3 and 4 and so on. You see that there are other simplices in there that simply are not accounted for. And then you can use this theorem that I've got here to actually reduce down and say, I can reduce the complex down to 2 to the n minus 1 minus 1. And then you see in there that there is a single simplex. A little hard to describe it here without access to a whiteboard, but indeed is what happens.
And then you get a persistent Maya-Viatora sequence in general, or something like that.
Well, so that's the other one. So that, so the cube analysis is what helps in doing, yeah. Say this: the cubes are being the necessary ingredient. So let me go to the end here. You're not going to be able to reduce, further beyond that by products from what we said. So the hope is this. So let me write it down. Yeah. So look. So the cubical complexes admit a presentation like this, right? So I have a bunch of cubes, Ci, and then the inclusions of their intersections, which are lower dimensional cubes. Mm-hmm. So the complex admits a presentation where I take the disjoint union of the Ci's and now glue together, faces, cubical faces, which belong to two different simplices them together. So there is a presentation like this, cubical complex. And, and again, if it's persistent, then it's persistent. And so now, what this is saying is, see, I'm keeping now input. I'm not going to try to do, to decompose the cubes. But what I'm going to say is that I want to take the cubes as my atomic gadgets, and I assume I go away into my closet and compute a persistent homology of all cubes. So I have that as input. But that's fine, as a list of spaces that one could deal with. And I say, oh, now the Vittorius Rips for this thing is going to be the same, I hope, one hopes, as the push of the corresponding diagram of Vittorius Rips complex is applied to the cubes. So you'll notice that on the lower part there, all I've got is Vittorius Rips complexes of cubes. And that's why I call it an assembly. It's like saying, I'm going to build the whole VR of X, only rips of cubes, and those things.
Okay. Yeah, and in the persistent setting, that this might be an isomorphism.
In the persistent, that this will be equivalent, but in a specific situation. So, roughly speaking, for convex sets of 1 to the n, the cubical complexes whose metrics are that.
Got it. All right, thanks.
Any other?
All right, if not, a very nice talk. Thank you.
Thank you.